So in the last class, we saw the arithmetic operators and we wrote basic programs to see the usage of these operators. Now let's go through the next set of operators, which are called as bitwise operators. Now the bitwise operators are primarily operators which will perform the operation on the binary equivalent of the number that you give as inputs. So bitwise operators will primarily work on integers because they will be converting the number integer into binary and doing the binary operation on it. Uh, Most of you are aware of what these operations are. So the AND symbol is used for AND operation. So a 0 and 0 is 0, 0 and 1 is 0, 1 and 0 is 0, 1 and 1 is 1. Similarly, we know OR, we know NOT, we know XOR. So I don't think we need to go into too much detail of these. Anyway, we'll see an example for them to understand how they work. We will go through what these are, right shift and left shift a little bit in detail. Now let me take the bitwise AND as an example. So if I'm performing an AND operation between the number, let's say 8 and 9. So this is if I say this is a bitwise operation, what we are trying to do, the binary 8, 0, 1, 0, 0, 0 and 1, 1, 0, 0, 1. So you take the binary of 8, you take the binary of 9 and then perform the AND operation. So if I take in this case 1, the 1 and 1 here, I'll get a 1, 0 and 0 I'll get a 0, 0 and 0 I'll get a 0, 0 and 1 I'll get a 0. So AND operation of 8 and 9 should give me 8. So the bitwise AND operation, when we use the ampersand operation, that is what it will do. It will take these two numbers, take the binary equivalent of it and do the AND operation and give you the output. Now remember, for any expressions that are executed on a decimal number, internally Java converts it into an integer. So we saw this in the yesterday's example of type promotion, right? So where the short and the byte numbers are promoted to integer values. So that means each of these are going to be actually 32 bit in length, right? So because we have everything else behind this is 0, we are not showing it. Okay, because we know 0 and 0 is going to be 0. So we are only going to get zeros behind it. So it's okay if we don't show these 32 bits, but just to remember, when you're performing arithmetic operations on decimal numbers, they are treated as integers, right? So they will be 32 bit in length. Uh, this is important, not might not seem very important now, but when we look at the right shift, left shift, we will see why this is a little important because now I might declare this as a byte in my program, but when I perform this operation, it will be treated as an integer. Okay, and we saw this in the last class. We executed a code to understand how that happens, right? So let's write a program for this quickly, how to do this operation. So let me open a new class. I will call this as and example. So it automatically creates a public class with the name of the file. So we have seen that. We will add the public static void main to it and the string args. So let's create two integer numbers. We'll take the same numbers for that we have used in our example. Let's say int x is equal to 8, int y is equal to 9, and let's perform the AND operation on it. So AND operation is equal to, sorry, call it as int 8 and 9, and let me print it out. System.out.println the AND of bitwise AND of 8 and 9, or let me put it in the variable format. Y is the value, and right, so that should do it. What is the error? Why it's showing? Okay, missed a plus, missed a plus. Let's see if the example that we took and the output that we get are the, I mean, how we solved it and what we get an output here are the same. So you can see the bitwise and of 8 and 9 is 8, and that is what we got in the output here, right? We got 8 as the output. So that's how the bitwise operations are performed. So similarly, if I say bitwise or 8 or 9, if we take, it will be similar two numbers. Uh, so let me just copy paste to make it simpler. So it's they are going to be 32 bit in length. So the initial zeros will remain as it is because 0 or 0 is 0. 1 or 1 is 1, 0 or 0 is 0, 0 or 0 is 0, 0 or 1 is 1. So we're getting 9 as the output, right? So if I create a new example for this, so same int x is equal to 8 into y is equal to 9, and we'll call it OR operation as integer is equal to 8 or 9, and let's just print it. Okay, let's execute that. You can see the OR of 8 and 9 is 9, right? So the symbol used is a single pipe symbol. For anyone who does not know where the pipe symbol is, it is the key right above the enter key. Okay, shift, hold the shift, and you can see the uh, above enter. You have the forward slash. Shift of the same key will be the pipe symbol. This is called as a pipe symbol, right? So similarly, you have bitwise not, which will negate all the numbers. So all the zeros will become ones, ones will become zeros. So I will leave you guys to try writing an example code for that. Similarly, the bitwise XOR will XOR the two numbers that we give. Again, the example you can write it yourself and test it, right? So uh, we will clarify if any doubts are there while you write the example. Now, the shift right operation you can see is two greater than symbols. So what do we mean by that? So the syntax for that is, let us say I have the number 8. Sorry, the number 8 and I want to shift right two times, right? So basically we have the 1, 2, 3, 4. I'm assuming that it's a 32 bit. I'm just writing the 8 bits here. The remaining 16, sorry, 24 bits are going to be zeros only, right? So this is my 8. You want to shift it right by two times, right? So shift it right meaning it has to shift towards the right side. You have done the similar concept before, and I guess you must have done it in your logic design. Maybe not. I don't know. Fine. So let's see what the shift right means. Just a second. Right. So that means I'm shifting in this direction towards the right hand side. So what is expected to happen? Let me shift it once. The first shift that I do. So initial numbers are zeros, nothing shifts. Now this one will shift to the right, so it will come here by one bit. So before that you have zeros, so you get a zero only before that, and you'll get 0 0. So this becomes binary 4, right? If you shift it again, this one will shift by one bit, so this will come here. So before that you have zeros. This becomes binary 2. So basically shift right is almost equivalent to division by 2. 8 shifted once becomes 4, 4 shifted once becomes 2. Alright, so this is the number that you want to shift, and this is by how many decimal places you want to shift. And before that, the zeros are there, so the zeros will keep filling in the empty slots. So if you have a number here, now let's run this example first, then we'll take the other possible case. So let's say you have example for, okay, let me write shift right example, right? So have, right, so now we want to shift something, right? So let me take a number, let me say x is equal to 8. I have created an integer, so I want to shift it twice, and let me assign it to integer y, and let me print it out. Shift of x by 2 bits is equal to whatever the result came, which is stored in the y, right? So let's print it and see what we get. So shift of 8 by 2 is equal to 2. You can see the answer 2, which is what we also got here, right? So basically you're shifting the number right by 2 bits, right? So one bit here, one bit here. You can give by any number of bits. Now let us say I'm shifting the number 9. Okay. Now 9 is this 1001. Now when you're shifting 9, the first shift, this 1 is going to be lost, because when you shift it right, this is not carry forward anywhere. So this one is gone. Right? So shifted right, you get 4 as the answer, one right shift of 9. The LSB is lost, right? Similarly, another right shift, you'll get 2 itself. Fine. So you have to remember that right shift, the rightmost bits, the LSB bits are going to be lost if you keep shifting towards the right. So the LSB bit is not taken anywhere else. You are going to lose the bit as you keep shifting towards the right. Right? So if I give the number 8, I'll give it 9 here. And if I run it, let's see if I get an answer as 2 itself. You can see shift 9 by 2 bits is equal to 2 itself. So shifting of 8, shifting of 9, both of them gave us 2. The reason being the LSB bit was lost when it shifted right. So when this got shifted, when this 0 1 came here, this 0 came here, this one was not sent anywhere, it simply got lost after the shift. So when you're shifting, you have to remember that the last bit, if there is a value there, it is not going to be retained anywhere, right? You are going to lose that value. Now, exactly similar to this is a left shift. So if you have a numbers, let me take the same number 8 itself and shift it left by twice, right? So so you want to shift it left. So basically you want to shift all the bits in the left direction. So everything has to move. So this should not. So you want to shift towards the left hand side. So the first shift to the left hand side, you can see this one will come here, this one, and this one will come here. Now the empty slot that gets generated here, that is going to be filled by a 0. Right? So this will become 0, 0, 0. Instead of this 0, I get this 1 because this is shifted towards the left. I get a 1 here. This 0 comes here, so you get a 0, you get one more 0. This 1 will come to this position, so I get a 1 here. The empty position that gets created here is going to be filled by a 0, right? So this number converted from binary should be this 0, 2, 4, 8, 16. So 16 plus 2, 18. So I guess we should get 18 as the result here. Let's see if, okay, sorry, I'm taking 9 here. This is 0, sorry. So it will remain 0 itself. So this is 16 then. Okay, so this uh, one shift is 16. The second shift, again, this one comes to this position, right? So the first two zeros remain as it is. I get a 1 here. Remaining zeros come as it is. So this is 0, 2, 4, 6, 8, sorry, uh, 0, 1, 2, 3, 4, 5. That is 2 power 5, which is 32, right? So actually the left shift is nothing but multiply by 2. So 8 left shift by 1 became 16. 16 left shift by 1 became 32. So you're basically multiplying by 2 when you shift towards the left hand side. Fine. So let's see if we get the same result if we so let me create a new class, shift left example, right? So add my public static void main. take a number, x is equal to 8, create another output variable y. Let's say you want to shift x 2 times and then print the result. So system dot out dot println the shift left of plus x by 2 bits is, add a plus and add the output variable, right? So let me execute this. You can see 8 shifted by twice is 32. So let's take a little more complicated example. So if I shift left 9 by 2 times, what will we get? So, so here the first left shift I'll get a 1 here. So this will become a 1. Second left shift I will get a 1 here, right? So 32 plus 0, 1, 2. So that is 2 power 4 should become 36, right? So let's see if we get the same value. And you can see the answer is 36. That is the binary equivalent of this what we got. So 9 shifted once left, 9 shifted left, left twice. Right. So that shift left is clear. There's another shift called as shift right with zero fill. Okay, this is only for right shift, not for left shift. There's a reason why this is used. Now, when you talk about decimal numbers, you can also have negative numbers, right? So let us say I have the number -2. Now, how is -2 represented? If you remember your digital logic, you would know that the negative numbers have the MSB bit is used to represent the sign bit, right? Uh, and the one at the sign bit there will be indicating negative number. And if you, for example, if you take the 2's complement of it, for example, if I want to represent it in a 2's complement format, so if I have 0010 is my actual number, the 2's complement of this would be 1101, and then so there'll be a lot of ones here because 32 bits are there. You'll have a fine with to which you'll have to add a 1 here, right? So 0000000. Not putting the whole 32 bits, I'm just taking an example. 1 plus 1 0, I'll get a 0 here, I'll get a 1 there, right? 1 plus 1 is 0, 1 comes here, remaining all ones remain. 1 plus 0 is 1, 1 plus 0, I'll get all number of ones here, right? So all of them will become 1 1 1 1 except for the last two bits. Now if you shift right this value, right, what is going to happen? You are going to end up getting ones into this. That is, if I shift this right, this 0 will go out and I'll get a 1 here, right? And these ones will keep shifting. Now, or maybe this was not the best example because everything is a 1 here. Let me take a slightly different example. Okay, let's not do this. Now, I'll just write. So, the negative number, remember that the MSB is 1. Okay, so you have the 32nd bit is 1. You can have anything else here, right? Any number of values here and some MSB, LSB value. Assuming these are the whole 32 bit, alright? So you have 1 to represent the MSB and the negative part of the number and everything else that you have here, right? Now, when you shift this right, what will happen is this one will start coming in. This one will start entering the number. So this will get filled by all ones as you keep filling towards the right, right? So to avoid that, right, that this one does not end up filling up all the places as you keep shifting towards the right, there's a type of right shift called as shift right with zero fill. That means whatever empty slot gets created after the right shift, fill it with a zero and not with the one that is coming from the sign notation. Right? So primarily used for signed arithmetic. Fine. So because in signed arithmetic you have a one here which is to represent the negative number, and if you shift this right, this one will start shifting continuously and you will have only ones coming into all the binary values, right? So to avoid this from happening, you have a shift right with zero fill, which says the empty slots that get created after the right shift, you fill it with zero and not with the sign bit that you have here. Fine. Now, to show an example for this, you can execute and see, but to check the actual output, you will have to write the binary equivalent of 32-bit length and then see what you get as an answer, right? So we'll just try writing it. Uh, Experimentally verifying it is little time consuming, right? Shift right with zero fill, right? So, because you have done this so many times, I'll copy it out. We have done this enough number of times, so you already know the basic syntax. So, let's say shift right thrice. See, in this case, this does not really make a difference. You can see that when the number is positive, you are going to get the same answer. Doesn't really matter. It's only when the number is negative, this is going to make a difference. So shift of -9 by 2 bits, you're getting some huge value here. Okay, that's what I said. It's a 32-bit value. To verify this, you'll have to check a 32-bit number, fine. But we'll just see the difference between the answer that we get if we use a zero fill shift and non-zero fill shift. So this is the answer we got when we use a zero fill shift. What is the answer we'll get if we use a normal right shift? The two answers are going to be different. So you got -3. Right? So that's the whole point. Here the ones remained. The one was always present. The one only kept getting filled. So because the one was always present there, the MSP one is always one, and it kept filling up all the one locations after that also as ones. So number will remain negative. All right. But in the case of all the numbers being one, I mean, when using the zero fill, you will not see that because you will lose the first one. Once it shifts right, it will be put with a zero there. Fine, so it will be not a negative number anymore. But primarily, you will not see this being used for arithmetic operations. It is used more in image processing. So just remember that there's a possibility like this available. If it's not very clear right now, it is okay. Don't worry too much about this. It is just an option available. Sometime if you see the requirement, you can keep it in mind that there is a right shift with zero fill where the MSP uh, which gets shifted, the empty slot will be filled with a zero, not with a one, right? So that just keep it in mind. That's right. So just let's write some example programs for this and try to understand the working of these operators, right? Thank you.